Hello, COGS 118B. On behalf of Nareg, Mallory, and myself, Robert, I present Neural Style Transfer. In Neural Style Transfer, we take the content of one image and the artistic style of another image, and we then combine them. This works remarkably well for any number of style and image combination. The idea of using deep learning in this application was pioneered by Gades et al. In their 2015 paper, A Natural Algorithm of Artistic Style. They were one of the first to use a CNN, or convoluted neural network, to separate the representative image content and the image style from within the picture. The network does this by starting with random noise and then changes pixels iteratively until it reaches the desired statistical feature distributions. Higher layers in the network form the content representation, whereas the style comes from the feature correlations of multiple layers giving the texture information but not the global arrangement. The input image is held as a group of filtered images within the CNN. The number of these content representations increases as you go up the hierarchy. However, the size of the filtered images decreases, meaning less total units per layer. Reconstructing the image from lower layers is almost perfect, and although higher layers lose some detail, they keep most of the higher level content. The style representations, as shown up on top of this image, are made from the correlations between the different features in the different layers of the CNN. There are two general methods for neural style transfer. One of them is descriptive neural methods based on image iteration, and the other is generative neural methods based on model iteration. The descriptive model was the first type of neural style transfer, and it works by updating pixels directly in the image for each iteration through the backpropagation, starting with random noise. This tries to maximize the content of one image and the style of another. The methods can be broken further down into maximum mean discrepancy and Markov random fields. The generative neural method is much faster than the first, but at the cost of some flexibility. A feed-forward network is trained on a large group of images for each style. Only a single forward pass is required using an image generator network and a loss network. Separate generative networks are needed to be made for each style. Current research aims to combine the speed of the generative model with the flexibility of the descriptive model.
So these are the dependencies that we needed to install in order for us to run our deep photo style transfer algorithm. VGG19 is just a pre-trained classification image tool, and there's more details on each of these dependencies on a link at the end of the slides. When we're running this program, we have to specify with both the flag for what the path we are giving is going to be, and then follow it by the actual path for the content image input and the style image. This is an example of how to run the deep photo style algorithm with certain passed-in parameters and their flags. On the right is the terminal screen with all the possible flags and the optional arguments you can use. As you can see, to the bottom left of the terminal, we are running this algorithm under a virtual environment with tensorflow so that the correct Python paths are used when executing the code. This actually gave us a lot of issues later on. Style option 2 specifies the type of photo transfer you're going to be doing. The total options you can pass in is 0, 1, or 2, and the details for what each of them do is on a link at the end of these slides. So this slide shows the input and output of our deep photo style algorithm. It takes as a first parameter an input that's the content image, in our case it's the yellow flower. The second parameter is the style image, which is the red rose right next to it, and then it outputs the style of the second parameter applied to the content of the first parameter, and it returns a non-distorted and correct color transfer photo as its result. Here's another successful run of our algorithm. The content image, the style image, and the output image with the correct applied colors and little to no distortion visible to the human eye. You can actually see some precision loss in the transferred colors by the sky color that's on the third stone head and the sky color on the first stone body. This occurs through content loss through the pre-trained image classification tool through each iteration. In this example, we used 2,000 iterations, and without the cluster, it took about 12 hours for us to obtain the final output image result. Our group wanted to do both different style images applied to the same content image, as well as different content images and applying the same style to them. An input that we chose to work with as in content image was the Geisel library photo. And we wanted to apply these style images to our content image in order to see how the algorithm would create a final output image result. We discovered that the deep photo style transfer algorithm we were working with already came with the segmentation input and segmentation style images, which is a middle step needed in the deep photo style transfer process. However, the algorithm did not have a process or source code for actually creating the needed segmentation images. This took a huge amount of our time because we had to search for a bunch of versions of algorithms to find a process for creating unique segmentation images for our unique inputs. Even though we found an open source with links to automatic segmentation imaging, we still had issues because the links were incredibly difficult to successfully follow. The links had source codes and documentation that expected that we already installed a lot of dependencies apart from the dependencies we had already installed for initial deep photo style transfer source code. And one of the dependencies needed was a MATLAB library environment that used paths from .mex libraries, and this did not match well with our prior installed dependencies like our TensorFlow virtual environment. The MATLAB source code that we were working with for our automated segmentation took a lot longer to get going than we expected. We had a lot of undefined methods that we were unfamiliar with, and they were undefined because we had incorrect library paths in MATLAB or we had missing dependencies, and in order to figure it out, it took us a while, and then once we believed it all to compile, we still had to test it with our segmentation inference on our main algorithm. So these slides show the output we were getting for actually our biggest problem, and that was when we were trying to put everything together in our virtual environment in TensorFlow and trying to actually get it to run on our unique inputs. And as you can see from the terminal, that we're again in our virtual environment TensorFlow, and this specific error out of the many that we received is having a problem with its split method, and neither I nor my team are very familiar with TensorFlow, so each of these errors we really had to dig through the library documentation to figure out what was going on, what should actually be passed in, and why it's incorrect. And every time we did try to fix it and try to make it work with our TensorFlow, it would actually give us another error. So this slide shows the result error that we received after we tried to fix from the previous slide, and we tried to make it work with our virtual environment TensorFlow, and we did that by using the documentation online. But every time that we would do this, we would receive another error, kind of more complex than the first, because again, no one on my team is really that, we're not really that experienced with TensorFlow. We're all fairly brand new to it, so this took a lot of our time, and with each error message we kind of got a little more confused because we just felt like it was just a circle we were running with, because fixing one error just gave us another. So this is a snippet of the document online we found for our virtual environment TensorFlow to help us figure out what we actually should be passing into our functions. So this is a screenshot of when we had errors with our methods in the MATLAB source code. We did end up believing that we have a segmentation mask with the correct libraries in place, but we're not sure because the main algorithm could not be running because of incorrect output from this source or because of dependency issues. This is just a link to the details and description of all our methods and results, as well as information about the dependencies.
Hello, I'm Narag and I'll be talking about the findings and discussion. Neural style transfer is the process of using convolutional neural network to migrate the semantic content of one image to different styles. The purpose is to recombine the content of a given photograph with the style of well-known artworks. The algorithm successfully produces fantastic stylized images with the appearance of a given artwork. The key idea behind this algorithm is to start from random noise as the initial result and then change the values of pixels until the desired statistical feature distribution is satisfied. These methods fit into one of two categories. The first category, which is a descriptive neural methods based on image iteration, transfers the style by directly updating pixels in the image, while the second category, which is generative neural methods based on model iteration, first optimizes the generative model and produces the styled image through a single forward pass. The biggest advantage of the algorithm is that it does not have restrictions for the type of style images, which has been the biggest limitation of previous approaches. The idea of descriptive neural method is to start from random noise and update pixels in the stylized image through backpropagation. Image iteration aims to minimize the total loss such that the stylized image simultaneously matches the content representation of the content image and the style representation of the style image. One of the keys is the predefined style loss function, which is optimized to match the feature statistics of the style image. One limitation of the descriptive neural method is the efficiency issue. The second category addresses the speed and computational cost issue at the expense of losing some flexibilities. Generative neural methods operate by training an equivalent feed-forward generator network for each specific style. The presented system consists of two components, an image generator network and loss network. Rather than using a per-pixel loss function, they propose the concept of perceptual loss functions. One limitation is that each generative network is tied to a single style, and separate generative networks have to be trained for each specific style image, which is quite time-consuming and inflexible. Because some paintings share similar paint strokes but only differ in the color palette, it is redundant to train a separate feed-forward network for each of them. Style representation called spatial style captures less style details and more spatial configurations. We can explore the neural style transfer algorithm by varying different experimental settings. The algorithm shows great results in transferring repetitive styles but often fails to transfer complex patterns. Space, color, and scale are three factors that can be controlled during style transfer. For spatial control, we may define a guidance map where the desired region is assigned 1 or 0. For color control, the algorithm produces stylized images of the color distribution of the style image. For scale control, we may separately study the scale control for style mixing and for higher resolution. In practice, the results produced by the generative neural methods are often not as good as the descriptive neural method. To help generative neural methods achieve comparable quality, we may swap batch normalization with instance normalization, which removes instance-specific contrast information from the content image. Other than instance normalization, we may establish a new loss function to improve the diversity of the stylized images. However, current neural algorithms do not consider the image depth during the process of style transfer. To address this limitation, we must add a depth loss function, which will measure the depth difference between the content image and the stylized image. For best results, current descriptive and generative neural methods usually require a tedious process. The optimization would likely improve if the parameter can be tuned with the aid of non-gradient information, such as magnitude of the losses or statistics within the losses. While there is still room for improving automatic parameter tuning for descriptive neural methods, the parameter tuning problem is more serious for generative neural methods, since a new model needs to be trained for each attempt of parameter tuning. Also, existing neural style transfer algorithms do not consider the brushstroke orientation control in many oil painting styles, which is an important element that cannot be ignored. It is able to impress the viewer and convey the painter's ideas. Nonetheless, the control of stroke orientation is difficult since detailed orientations and continuities of curves and results are hard to guarantee. Current algorithms are based on feature statistics. Algorithms produce visually plausible results for the stylization of generic images. It is not appropriate for head portrait style transfer. It does not impose spatial constraints. Directly applying these algorithms to head portraits often deforms facial structures, which are unacceptable for human visual system. One extension would include the use of gain maps to constrain spatial configurations, which can transfer the texture of the style image while preserving the facial structures. Another work aimed at extending the algorithm from still images to video sequences is a neural video style transfer. Given a style image, the algorithm introduces a temporal loss function to transfer its artistic style to an entire video. The key idea behind the algorithm is to use a temporal constraint to preserve smooth transition between individual frames. The algorithm is shown to eliminate most temporal artifacts and produce smooth, stylized video.
Here's a list of some of our citations and resources, and we'd like to thank Professor Desa, our TAs, and you, our wonderful audience.